Today
Yeah.
we have Naomichi Hatano, and he will talk about or answer the question, what is the environment in an open quantum system?
Okay.
When you're ready, go ahead.
Yeah. Thank you. Thank you, Andreas, and for organizing this. And I hope I can convince you that the environment has two roles here. It provides detectors and it generates non-hermiticity. Okay, so first of all, what do I mean by open quantum systems? So by open quantum systems, I mean some big system with the total Hamiltonian H is generally Hermitian, okay? And but I'm not interested in the total big Hamiltonian. I'm interested in a small part of the total Hamiltonian, which I refer to as system Hamiltonian. And then the rest is I call environmental Hamiltonian. You see, environment must be green. So that's why I put green here. And as I said, the worst point of the online talk is I can't hear your laughter, so I put laughter myself. And so here is this coupling Hamiltonian. And if I typically assign P for the projection operator for the system Hamiltonian and Q for the environmental Hamiltonian. So so system Hamiltonian is PHP, environmental Hamiltonian is QHQ, and coupling Hamiltonian is this. Okay. I'm gonna use this notation later on, but in the first part, I'm gonna focus a bit more on a more specific situation where the system Hamiltonian can be complex and non-uniform and finite, while the environmental Hamiltonian is simple, uniform, and semi-infinite, and it can have many channels, several channels. And a typical example is nuclear scattering. So, in fact, it generates this kind of nuclear diagram. So in this case, this nucleus is a system Hamiltonian, and this free space surrounding the nucleus with one single neutron is environmental Hamiltonian. That's simple. And it has many channels with the spherical modes of the neutrons. Okay, so that's what I meant in the previous slide. Okay, here are some condensed matter examples. I have some on a semiconductor, electrons can be almost free electrons, and the free electrons can come into this narrow channel, can have some, this small part can have complex structures, but it can go out into free space again. Okay, so this is a particular open quantum systems I'm interested in. Okay. Now, and this is an open circulatory system, not quantum. But so here's a open quantum system. But as you saw, it is actually not really semi-infinite. I mean, because the whole system cannot be semi-infinite. Actually, it's actually terminated by detectors, right? So can we really have real open quantum systems in this kind of experimental setup? That's my first topic here. Okay, and now we can rely on the Landauer formula. This is Rolf Landauer. And some condensed matter physicists here are familiar with it, but let me talk about it a little bit later, So Landauer formula tells you the conductance or the inverse resistance of this some quantum scatterer sandwiched by two electrodes. Okay. Now this quantum scatterer, this is in this case, this is free space, and here are some impurities or quantum scatterers, and you have positive electrode and negative electrode, and the Landauer formula tells you that the conductance or inverse resistance between these two electrodes are given by the transmission probability of this quantum scatterer. Okay. But transmission probability is not computed in this setup. Transmission probability is computed in this setup, right? So why the physical quantity of this situation is given by this situation? That's because in this situation, electrons that leave the quantum scatterer and came into the electrodes never return to this quantum scatterer in a coherent way. Okay, and in this setup too, electrons once leave this quantum scatterer never comes back. Okay, so that's what's common to these two setups, which I can term as completely absorbing boundary condition. And so that's why the physical quantity of this above setup can be given by this transmission probability in this setup. Okay, so that's why even if in the experimental setup we have detectors or terminators here, but we can still talk the physical phenomena in this semi-infinite in this infinite situation. Okay, and now I'm shifting the topic to the resonance state, because this is exactly what we compute the resonance state. Okay, and this is another topic I often talked in this series of conference, but I've never talked in a coherent way, perhaps. So that's why I think this is a good time to review. Okay, and this is the definition, typical definition of textbook definition of resonance is a pole of transmission probability. Okay, but I can give you another more sophisticated definition. Okay, so suppose we have some scattering problem. This here is an incident wave and reflection wave, transmission wave, and transmission probability, which is according to the Landau formula, is proportional to the conductance, sometimes has resonance peak. Okay, and we know that if we analytically continue the energy into the complex energy plane, then actually the resonance peak has a pole in the complex energy plane, and that's the resonance. Now, but at the resonance, so the denominator, when this has the pole, that means that the denominator has a zero here. Okay, so we can find the wave function of this pole at this pole from the very beginning by assuming this vanishing incident wave, right? So this is actually the wave function at this pole, and this wave function is actually defined by Siegert in 1939, and so he defined the resonance as an eigenstate of the Schrödinger equation under completely absorbing boundary condition. Well, usually we call it outgoing wave boundary condition, but what happens is actually completely absorbing boundary condition. Okay, so so suppose you solve this Schrödinger equation with this the standard potential, and you have these boundary conditions, and which I typically write in this way. Okay, if you solve this, then well, this is good homework for you. But what happens is I can find all these solutions. Okay. Now this is a complex wave number plane, and this is a complex energy plane. And here is a bound state. You see, so if wave number is pure imaginary with a positive imaginary part, if I insert this into here, then you'll see Mount Fuji bound state here. Okay, so this is actually a bound state, and actually this energy is a negative, slightly negative real number. Okay, but solving the problem, I find, well, there are scattering states here, but solving other discrete solutions here, resonance state, and I call it anti-resonance state here. Okay, and what are the physical meanings there of these states? Now I wrote the wave functions of these states like this, but if I add the time dependence here, then the physical meaning becomes more clear, because for these red states, okay, for these red states, the eigenvalues have imaginary, negative imaginary parts, but wave number have real, positive real parts. So this means in this wave function, wave number has leaks, outgoing waves into here, and then the captured probability decays in time. Okay, so if I have a negative imaginary part, then that means here decay in time, right? So this is a resonance state as an eigenstate. It decays in time, and the probability leaks into infinity in the outgoing waves. That's the resonance state. And then anti-resonance state, these green states, is actually the time reversal of the resonance state, because now imaginary part of the eigenvalue, energy eigenvalue, is positive. And so if you insert here, it grows in time. And the real part of the wave number is negative, which means waves are coming in like this. Okay, so this is an anti-resonance state as an eigenstate. Okay, so I could say that the resonance state is actually a decaying solution, and anti-resonance state is a growing solution. And the point is, although the original Schrödinger equation is time reversal symmetric, each resonance state or anti-resonance state breaks the time reversal symmetry spontaneously. Okay. Now, here is a question. Okay. Question 1, which is which probably many of the audience here is familiar with this answer. Okay, so Hamiltonian is time reversal symmetric. Schrödinger equation is time reversal symmetric. Then why the eigenstate breaks the time reversal symmetry? Okay, if they commute with each other, then they must have simultaneous eigenstates. Well, Carl should know the answer. So suppose H and T commutes like this, and if you'd have this, then in fact T is also the eigenstate of the Hamiltonian with the same eigenvalue. So we would have this, but in fact T is an antilinear operator. So this is the answer. This is the correct answer. So if E is real, then we would have this. But if E is complex for like this, then this means that if you have a resonance state with a complex eigenvalue, then time reversal of that resonance state, which is an anti-resonance state, it has a complex conjugate eigenvalue. So this symmetry is actually the time reversal symmetry. Okay. Okay. So next question. Why can complex eigenvalues appear out of a Hermitian Hamiltonian? Okay. Some of you are also familiar with the answer. Well, so here V is a real potential, and this is the standard, kinetic energy. So this Hamiltonian is must be a Hermitian Hamiltonian, isn't it? Well, actually, it can be non-Hermitian because Hermiticity or non-Hermiticity depends on what functional space you define the Hamiltonian. Okay, so in elementary class of quantum mechanics, the teacher tells you, okay, this is Hermitian because if you take the element, the matrix element with arbitrary function, then that's the matrix element is real. So that's why this is that proves that this is Hermitian. Okay, but actually there is a hole in the proof. Okay, so suppose, well, actually the non-Hermiticity comes out of this kinetic energy term. Okay, so suppose you take matrix element of this kinetic term, and just in case you don't take the minus infinity to the integral over minus infinity to infinity, just to make sure you take a finite range integral, and then if you can take L to infinity, take the limit of L to infinity. Okay, so here this is integral, and if you do partial integration once, then you end up with this. The complex conjugation of that is given by this. I move this complex conjugation here, and the partial integration once have this. Now this and these are real. Okay. So if you subtract below from above, then the imaginary part of this matrix element is given by this boundary term. And the teacher always tells you, well, we are interested in normalizable wave functions. So if you take L to infinity, then this would be 0. So that's how you can prove the hermiticity of this. But for resonance state, actually you can't say that, because in the resonance state here, imaginary wave number imaginary part of the wave number is negative, which means that if you insert the negative imaginary part here, in fact, you have this kind of wave function, diverging in space, okay? So in this kind of functional space, Hamiltonian is actually non-Hermitian and can have complex eigenvalues, okay? So that's, so because this cannot be zero in this kind of functional space. Okay, so so the answer to this question is, well, the seemingly Hermitian Hamiltonian, this, can be non-Hermitian in a wider functional space. And so in other words, the non-Hermiticity is hidden in the environment. Okay, so that's the answer to this second question. Well, you have more question? Well, of course, because then what does the diverging wave function physically mean? Actually, so this diverging wave function is the reason why many people call it unphysical states because some people don't believe the wave function in the lower half of the complex eigenwave number, because and they call it the unphysical part of the eigenwave number. Okay, because it's not normalizable indeed. Okay, but I'm going to tell you that we still have the probability interpretation. And so it's not normalizable, but we still have the probability interpretation. Okay. Now, here, because we have this kind of wave function with this kind of time dependence. If we have the probability of this wave function has this diverging term, but this decaying term. Okay. So in the resonance state, suppose we compute the probability, we integrate over the probability density over this finite range. Okay. And so compute the probability that lives inside this finite range. Okay. Of course, it continues into here, but still just restrict yourself into this finite range. Okay. After some time, because of this, you remember in the resonance state, the probability leaks outside. Okay. And probably the velocity of the leak is given by this. Okay. So after some time, you expand you should when you should count to make the proper definite to track the probability density. Then you have to expand the integration range according to this velocity. So you expand in time the integration time range according to this velocity. But in the meantime, because of this factor here, it decays like this in time. Okay, and actually we can prove that this kind of this integration over a finite range does not depend on time. It's constant. Okay, so this actually gives you the probabilistic interpretation of this kind of diverging wave function. So this probability is still conserved here in the finite range. Okay, So this means that actually diverging wave function supports the probability interpretation, right? Without the divergence, you don't have that probability interpretation. It diverges in space, the wave function diverges in space, but decays in time, and that's how it keeps the probability interpretation. Okay, so it's physical, and but it's more physical in the sense that in reality we have detectors, right? And completely absorbing boundary condition. So a macroscopic number of particles are in fact absorbed by the detectors, and that's why it diverges in space, and in the end macroscopic numbers of particles are finally absorbed by the detectors. And that's what this diverging wave function physically mean. Okay, so I've talked about this kind of situation, and so far my summary in this first part is, well, environment provides a completely absorbing boundary condition, and because of that, environment generates the non-hermiticity in this open quantum system. Okay. So this is this is the first part, and then I'm going to the second part because time flies like an arrow. And in the second part, I'm going to talk about the Feshbacher formalism. Feshbacher formalism tells you the way to eliminate this infinite environment, semi-infinite environment, and eliminate it and make it into a non-Hermitian effective potential. Okay, I'm gonna tell you some algebra now. Okay, so I'm coming back to this situation now. So here's the total Hamiltonian. H is Hermitian in this case, and here's the system Hamiltonian is PHP, environmental Hamiltonian is QHQ. This is the PHQ, and QHP is the coupling Hamiltonian. Okay. Now, what I'm interested in is, of course, I want to solve the Schrödinger equation of the entire system, but I'm only interested in what happens in this P subspace. Okay. So what I want to do here is to find the Schrödinger equation only for this P, the wave function for this P subspace. Okay, then what would I have for this effect of this part? Okay, so this is the Schrödinger equation for only for here. Then what would I see here? Okay, so that's the algebra. Now I first apply a P projection operator for this, and insert P plus Q here. Okay, P plus Q is identity, of course. Now this is then I apply Q operator, Q projection operator to this, and insert P plus Q here. Okay, so I have two equations now. And then I simply rewrite this in this way. Okay, so this equation, this first equation has P psi, but Q psi here. And this second equation has Q psi, but P psi here. So what I'm gonna do is, from the second equation, I find Q psi in terms of P psi. Do you find this? So I move this second term into this, okay, and then divide it with this. Okay, that's what I did. Okay, and so I find Q psi in terms of P psi, and I insert this into here, then this equation gives the equation completely for pip psi. Okay, so that's the algebra. So if I insert this, then I find this. Okay, do you agree? Then, so comparing this equation with this, or this equation that I wanted to find, I find that the effective Hamiltonian is this. Okay, then I always, in the past, I kept this, I kept calling this non-Hermitian Hamiltonian, but once I was asked by Yogesh that, well, this is Hermitian, isn't it? But because, you know, these are all Hermitian. Well, the answer is this is not really, well, it looks Hermitian, but the trick is it here QHQ is a very large, well, infinitely large subspace, Hamiltonian infinitely large subspace, and so you have to take care when you have to be careful when in computing this Green's function. Okay, because QHQ has a continuous spectrum on the real axis, so you can't really compute this directly. What you have to do is to define either retarded Green's function or advanced Green's function. So you have to insert this small term in computing this. Okay, so this in fact makes this effective Hamiltonian non-Hermitian. Okay, so what does it mean actually physically? If you reuse retarded Green's function, this retarded Green's function actually means that, you know, you have outgoing wave. Advanced Green's function means incoming wave. Retarded Green's function means outgoing wave from this contact. Okay, so in fact, using retarded Green's function provides you a completely absorbing boundary condition. So using the retarded Green's function in the computation of the effective Hamiltonian is actually equivalent to the computation of the wave function in the completely absorbing boundary condition that I talked in the first part of my talk. Okay, so if I use the retarded Green's function here, then I actually find these states after properly diagonalizing this effective Hamiltonian. Okay, well, you see, I have here it's the imaginary infinitely small negative imaginary part, but after the proper diagonalization of this effective Hamiltonian, this infinitesimal imaginary part is enhanced into a finite negative imaginary part. That well, I don't have probably I don't have time to say this, so I just I don't talk about that. But because of this negative imaginary part, finally we have a finite negative imaginary part. And if I use the advanced Green's function plus here, then I would have this. Okay, and that's because this corresponds to the outgoing wave Green's boundary condition, and plus advanced Green's function corresponds to the incoming Green's function, wave function. Okay. So in the So in the second part, I talked about this Feshbach formalism, and I told you that this environment, if you eliminate it, in the first part, I said that non-hermiticity is hidden in the environment, but if you eliminate this environment, then you end up with the explicit non-Hermitian Hamiltonian. Okay, so that's the point of the second part. Again, environment provides a completely absorbing boundary condition and thereby generates non-hermiticity. Okay, so in the remaining time, I actually want the comment on the Bra vector. What is the proper definition of the Bra vector? And the reason is I use the Bra vector as the Hermitian conjugate of the Ket vector. Most of you are more familiar with the another definition of the Bra vector, so that's why I'm making a comment here. This is according to private communication with Kohei Kawabata. Okay, so just consider simple non-Hermitian matrix like this. Okay, so it's basically a two-side model with the hopping element greater in this direction than this direction. Okay, so the Hamiltonian is like this, and you can just compute easily that the eigenvalues are plus or minus 2, right? Okay, and you can easily find that the corresponding right eigenvectors are this and this. Now, you can see that they are not orthogonal to each other. So, to make something orthogonal, you must compute the left eigenvector of this Hamiltonian 2. The left eigenvector of this Hamiltonian for this eigenvalue is this, and the left eigenvector of this Hamiltonian with this eigenvalue is this. So indeed, this and this is orthogonal to each other. This and this is orthogonal to each other. That's called bi-orthogonality of this non-Hermitian Hamiltonian. But I didn't use this this Bra vector. Okay, so I put tilde here because this is actually not Hermitian conjugate of this Ket vector. This Bra vector is not Hermitian conjugate of standard Hermitian conjugate of Bra vector. So that's why I put tilde here. But in the argument past, for example here, I didn't use that Bra vector. I simply use this standard definition of the probability. Okay, so here the Bra vector I'm using is simply the Hermitian conjugate of the Ket vector. Is it consistent? Well, actually, it's consistent in an open quantum system. Okay, so that's why I wanted to make a comment here. Now, in the open quantum system, well, typically the total Hamiltonian itself is Hermitian. Okay, so the wave function like this, and another wave function, eigenfunction of this total Hamiltonian in this space, psi1, and another eigenvector in this total of this total Hamiltonian in this whole subspace should be orthogonal to each other. So if I integrate over integrate this quantity over the entire space, then it must be zero. It must be orthogonal. But you see, I was only interested in this system Hamiltonian. And in fact, if you compute this quantity, if you integrate this quantity over only this subspace, then of course this is not zero. So it's natural that the wave function eigenfunction are not orthogonal in this small subspace, but that's okay, because still this has the meaning of the probability density. Okay, so that's why I used this definition as the probability density. Okay, so so it really depends on the physical interpretation of your Hermitian, non-Hermitian Hamiltonian. If you think your non-Hermitian Hamiltonian is the whole space, your whole space, then of course you have to consider, you have to use the bi-orthogonal basis. But if your non-Hermitian Hamiltonian is only is non-Hermitian only because it's a part of the Hermitian Hamiltonian, then this is fine. Non-orthogonality is fine. You still use this as the probability, as the definition of the probability density. So, and I'm making this comment because I saw the other day some mistake in the seminar, so that's why I'm making this comment. Okay. Okay. So summary. So environment of an open quantum system provides a completely absorbing boundary condition on behalf of detectors, and thereby generates non-hermiticity. That's what I kept talking in the first part and the second part. Okay, thank you for your attention. Okay, questions? Yeah. Questions?
Yeah, I have a question.
Sure.
Okay.
How about the fluctuation dissipation theorem in your formalism? Does that drop out?
What do you mean by fluctuation dissipation theorem?
Well, if I understand your system, your universe, it's that you have some dissipation. So you're losing particles from your system and they're going into the environment.
Okay. Yeah.
And of course, this isn't the most general environment. I mean, you could have the environment sending things back in.
Yeah.
Like a dynamic bar. Let's ignore that for a second, but I would still expect, under sort of very general sort of reasons, that I would get some sort of fluctuation dissipation theorem. So if I have dissipation in my system, I should expect that to introduce fluctuations.
I'm not sure I got your question. So what do you mean by fluctuation? Well, so usually fluctuation dissipation theorem means that so response of some system is given by the correlation functions. That's my idea of fluctuation dissipation theorem. So I guess I don't understand your idea of fluctuation dissipation theorem.
Well, think of, I'm thinking, I mean, one of the simplest examples is the Langevin equation. where you might have some frictional term and some decay, but then you need to put in some fluctuations, some noise. That's the sort of the random term in the Langevin equation. And I'm just wondering if that exists.
So random term is actually, random term effectively appears from the fluctuation from the environment, right? I mean, it's random term appears because there is a environment there is an implicit environment. So for example, Brownian motion.
Yeah.
So Brown particle is fluctuates because there is an environment. So, and if you compute if you take care of the environment exactly, then you don't need this random fluctuation, right? I mean, so if you keep track of every motion of water molecules banging the Brownian motion, then you don't need the random force. So the that kind of random thing comes from the environment, and is
that included in purely absorbing boundary conditions, I guess, is my question.
What's the question again?
Well, with your purely absorbing boundary conditions, which are not the most general boundary conditions one could have, does one still get this rather fundamental relation of the fluctuation dissipation theorem? I wonder, these Green's functions you had, if you calculate the imaginary parts of them, and that give this fluctuation dissipation theorem, I wonder if it all just drops out nicely in the Feshbach formalism or not. It may well do.
First of all, maybe maybe you're talking. Maybe we are talking about two different things. Here, I'm ignoring the interaction between particles. Okay, so this is basically one particle problem. So maybe I can't have any fluctuation dissipation theorem here because we don't have any interactions between particles.
I think even if you have a cavity, an optical cavity, and you have photons, you have a photon field inside it, and you just let the photons leak out of that cavity, you still get noise. And one way to see it in quantum optics is through the sort of vacuum entering the cavity from the sides, and that is one sort of mechanical way in which explicit way in which you can see the noise come into the system. And it's due to, as you say, it feels the modes outside that the photons are escaping to, and that's completely non-interacting. It's a linear problem, but you get.
Okay, I see. Okay, I feel now another difference between what you're talking and what I'm talking here. So you are probably talking about the dynamics, time independence. But here I'm talking about the eigenvalue, time independent Schrödinger equation. So the dynamics is expanded in terms of all these eigenvectors. Okay, so to properly describe the dynamics like that, like you're asking, I probably have to take infinite sums of these eigenvectors. So I guess I can't answer your question properly because I haven't done it. But that's probably the biggest difference between what you're asking and what I'm thinking.
Maybe.
Okay.
Yeah, I forgot to say, beautiful talk, by the way.
Oh, okay. Thank you very much. Yeah.
Yogesh wanted to add something to this discussion. Yogesh, you're on mute.
Yogesh?
All right. Are you able to hear me? Okay, I think
Yes.
it should be. Yeah. Thank you, Naomichi. I really enjoyed the talk and particularly the explanation of how the non-hermiticity comes about. And I think regarding Duncan's question, I think that the way I would think about it is that if you have perfectly absorbing conditions, then it's essentially connected to a zero temperature bath. You have fluctuation whose variance goes as the temperature of the bath. And so as long as you are connected to zero temperature bath, then this formalism is accurate because stuff goes into the bath but never comes back. This is all lossy system.
Oh, I see. Now I
no
see.
Fluctuations. Yeah.
Right. Okay. Now I can see the proper answer. So here I'm talking about the Schrödinger equation, but to obtain the fluctuation dissipation theorem, I have to talk about the von Neumann equation instead of the. So I have to talk about the density matrix, the dynamics of the density matrix instead of the Hamiltonian. This is all about the pure state, but I have to talk about the dynamics of mixed states if I need if I want to derive the fluctuation dissipation theorem. Okay, I see. Thank you, Yogesh. I think that's the proper answer for Duncan.
I have two comments or maybe a question. It's Frieder Kleefeld. In the last slide before the in the second last slide, you wrote down this non-orthogonality of the wave functions.
Here.
One more.
Now
one more. Yes, now we are here. Yes, here. I think this notation is confusing because you put the projection on the integration volume. This suggests somehow that the space is divided by the projection, but the projection goes on the wave functions and not on the integration volume.
Oh, sorry.
Notation is. You consider an atom. The way how it is taught in university classroom physics is that you somehow calculate stationary atoms, and then you calculate transition probabilities between states, and you assume somehow that the widths of your states are very narrow, and the atom is not changing by a transition. But what is happening, and you integrate over the whole space volume. But when an atom somehow makes a transition into another state, the atom is not the atom alone, but it's also the electromagnetic field, which is somehow here your environment. And in the initial and the final state somehow are not the same atom anymore, is not the same atom anymore what you have at the beginning. You started your talk with a nuclear physics example where this particle scatters at the nucleus, where you say that somehow the nucleus is the system and the particle scattering is somehow everything around. But in nuclear reactions, very often you start with one nucleus and a scattering particle, and then in the end you have another nucleus with another scattering particle, and you have somehow the field interacting. So the whole system is somehow a sum of everything, and it changes through the time. So this simple separation between the system and the environment is not so crystal clear as you describe it by your projection, because somehow the projection changes over time. Yeah. And this may complicate the situation.
No. That's a typical difference between what people have in mind and what I'm talking about. So I'm talking about the time independent picture of the Schrödinger equation. Okay, so you are talking about the time dependent picture of the Schrödinger equation. Okay, so here in the nuclear scattering, you have the nuclear Hamiltonian, and here neutron Hamiltonian, and here's the interaction. But you don't ask the time evolution. You simply find the eigen functions of that Hamiltonian. And when you want to describe the time evolution, then you expand the time evolution in terms of these eigen functions. That's the so this is talking about this in a different terminology. Okay.
Right, but you are talking somehow about transitions probabilities or conductances or something, and they suggest somehow that your system doesn't change over the time, yeah. And
right.
At the same time, you have, if you have a particle scattering at the nucleus, somehow both systems be distributed over the whole space, and not saying the one thing is outside and the other is inside. So if you do your projection, you make somehow a projection on the quantum numbers and the eigenstates of the system, which may change over the time, and the interaction carries some energy in the whole picture, which should also be seen. Huh? But I think the general picture you describe here is really the true picture. But I think there is a bit more if you have really, for instance, atomic decaying atom, as it is described in the classroom. I think it's not complete, because you have this evolution of the atom into another state, and you should never forget the energy of the electromagnetic field in the whole atom, which is usually neglected when you just solve the Schrödinger equation. Yeah.
Well, okay. I admit that, you know, I'm not talking about the details here. So, for example, so in this I'm not considering any transition from one atom to another, one nuclei to another nuclide. In this picture, after infinite time, the final state should come back to the initial state. You
Yes.
know, so that's what in this picture. That's what should happen in this picture. And so I'm not talking about the transition to any other thing.
I have one more little question about your Feshbach effective Hamiltonian. Maybe you have the transparency there.
Okay, wait a sec. Feshbach.
Yes, and you were diagonalizing it and showing the eigenvalues, the resonance.
This one. This one.
Yes, yeah. And you said you diagonalize it and solve it for these eyes, but this is a highly nonlinear equation. How do you solve such complicated systems to get these without taking the wave functions? I mean, you need some wave functions, no?
Right. Okay. So you are right, and thank you for the question. I didn't explain it, but this is nonlinear because, you know, this equation is nonlinear eigenvalue problem because this also depends on energy. Okay, so energy is on here. So that's your question, right? Okay, right. And now I typically consider, because I'm condensed matter physicist, I typically consider tight binding model, lattice model, and in lattice model, actually, I can have this nonlinearity is actually up to second order. Now, second order nonlinear eigenvalue problem can be cast into a linear eigenvalue problem by doubling the space. Okay, so in this case, if you consider the infinite continuum space, then you can't really linearize it by making double. You have to make infinite hierarchical equation of motion, but that's how, I mean, well, you cut off somewhere, and that's how you linearize this equation, nonlinear eigenvalue problem. And that's how, as I said, that's how this small non-hermiticity is enhanced in the end. Okay, but thank you for the question. Yes, that's the point. I didn't like. Yeah.
If I may add a comment.
Hi. Yeah.
So there is this energy dependence, which is crucial in this transparency, which we see now.
Mm-hmm.
And the easy answer, without going to complicated models with environment being continuous spectrum and so on, you may consider the big Hamiltonian also in the form of finite matrix. In this case, this Hamiltonian looks self-adjoint, and it is not for another reason. I mean, it is not because of this eta, but because of the fact that you have spectral representation for this effective Hamiltonian, which you may write in principle, where the separate eigenstates are not mutually orthogonal. That's the point. So that's my comment. You may even argue that it is not a Hermitian operator because even in finite dimensional matrix models, this energy dependence makes the eigenstates not mutually orthogonal. So it is the reason why the
right. Yeah, well, mathematically, it's the reason. Yeah, I was just talking about the sort of a physical way of thinking that non-orthogonality, and so that's the wave function. The wave function is orthogonal only when we linearize it by doubling and tripling the space. And but you're right. If this is energy dependence, then these are not orthogonal to each other. And but that's I mean, this is a physical way of saying that. Okay, I think.
Yeah, I must add that I absolutely admire your presentation, because you just were able to say just the essential things. I mean, there are technicalities which you may forget, but you just spoke about the essence of the problem. So absolutely marvelous. Thank you.
Okay. I'm glad you enjoyed it. Yeah.
Saikat Banerjee has a question in the chat. Saikat, you want to ask the question?
Oh, hi. Yeah. Actually, I was wondering if there is a connection to the Lin-Palladian approach, because in non-equilibrium systems also there is this.
Say it again. I didn't catch it.
So, I mean, what I found is this. So there is a big environment and a small part you are interested,
Mm-hmm.
and then there is effective Hamiltonian H effective. So I was wondering if there is any connection to the master equation approach when people also study these non-equilibrium systems.
What do you mean by master equation approach?
Like, I mean, yeah, if I have a big system which is coupled to, and then I'm interested in a small part of it, let's say pumped typically the pumped systems like non-equilibriums. And so of course it's time dependent, but then one can look for steady state solutions. And in that case, I guess there is this master equation approach. I mean, so one focuses on the density matrix of the small system and tries
Are you talking about the quantum master equation or classical master?
Yes.
Hmm?
Yes.
Quantum master equation.
Yes.
Oh, okay. So okay. That's another interesting question. So if I Fourier transform this effective Schrödinger equation into the time dependent equation,
yes,
then actually because of the energy dependence of this effective Hamiltonian, I find non-Markovian kernel, memory kernel. Okay, so generally, because of the energy dependence of this effective Hamiltonian, if I Fourier transform into the time domain, then this is a non-Markovian Schrödinger equation. But if to obtain the quantum master equation, I have to approximate that non-Markovian memory kernel with replace it with memory forgetting Markovian equation. So that's how I can obtain the quantum master equation. So to obtain the quantum master equation from this, we have to make a Markovian approximation. It's not equivalent.
Okay.
Thank you.
Any more questions? Should we then all unmute and thank Naomichi for the talk?
Okay.
Thank you, Naomichi.
Thanks.
Thank you very much, Naomichi.
Thank you.